Okay, let's do it. Take it away. Oh, sorry, let me refresh that. Go.
Hi, I'm going to talk about FPLIP, which is a fixed point math library for System Verilog that we open sourced. So let's do an example. Let's say you want to do y equals m times x plus b, just a multiply and add. But let's say all of these four numbers are fixed point numbers, so the number of integer and fractional points are supposed to be fully parameterizable. The format is arbitrary. If you've ever done this in System Verilog, it's going to look something like this, about 30 lines of code. All we wanted to do is a multiply and an add. And also, if you want to debug this in the waveform viewer, you just have these huge integers, and it's kind of hard to debug without a lot of mental math. So VHDL has a solution for this. There's an IEEE fixed point package, but System Verilog doesn't. So FPLIP is trying to bridge that gap. So it makes it really easy to do fixed point math, multiply, add, subtract, and it takes care of all the little details like shifting the binary point and truncation and clipping and zero padding and whatnot. So the way it works is that we kind of abuse System Verilog interfaces, and we kind of put the bit vector, the logic vector, and the parameters for the number of integer and fractional bits into this interface, which is kind of like a type that you can pass through the module boundaries. So if you were to do the previous example in FPLIP, you just need like 3 lines of code. Also, the bonus is that when you go to debug this in the waveform viewer, it's really easy because you actually get the floating point representation of your numbers, at least in RTL sims. So it's tested with, we've taped out a chip with this. It works in Cadence tools, goes through synthesis, all that. And it also works with AMD Vivado. Not sure about other tools, but if you try it, let me know. So it's up on GitHub. You can use it in commercial projects, and contributions are welcome.
Cool. Cool. Thank you. All right.
All right.
Let's go. Oh, you've already got. Okay, cool. All right. So. All right.
Ready to go?
Ready to go? Go.
All right. Hi, my name is John McMaster, and I'm going to talk about Fossaf Silicon. And skipping ahead a little bit. So basically, here's the elevator pitch. So about 3 months ago, I left my full-time job, and I wanted to do something that was kind of technical but low stakes. I do some silicon inspection, like metrology, and sometimes I've done some chip design stuff, but I've never done actual nanofabrication. So inspired by things like CMU's HackerFab, Jerry Ellsworth, and others, there's a group of us that want to see what is the current state of the art of garage chip fabrication. So kind of a loose-knit group of about 10 people working on different parts of this and trying to see what we can do to raise the bar in this field. First bit is we're like, let's build a spin coater. I don't know people, different backgrounds, but basically when you do photolithography, to project your masks onto something, you need a photoresist. This is the tool that puts the photoresist on. Open source project, pretty cool, but it got abandoned. So what we're trying to do is basically fix it up. And my goal is to maybe get 100 of these out there. So if you're interested in spin coaters, open source, 3D printed, hit me up. Next thing, we got a fellow who's making a tube furnace. So you got to bake those dopants in there. So you can see a few different revisions. He's got his little first version, and you see like the next, I think third revision there is getting a little more mature. So that's how you get your dopants in there anyways. Next thing, we want some automation because everybody loves robots. It looks cool, the fab's moving around. It's fun. So on Crowd Supply right now, a lot of 3D printed parts, open source, both the CAD models, firmware, everything on there. He's got some cool factory automation stuff. He's in Chicago, not San Francisco as much, but still pretty cool. Also working with various open source, a lot of 3D printed microscope technologies, because we have to do metrology. We have to make sure the chips work after they've been fabricated. Are the critical dimensions correct? Maybe do some wafer probing, kind of stuff like that to actually get a feedback loop. So we've been exploring different projects to make that happen. But last but not least, you need lithography. So ours is based on Carnegie Mellon's HackerFab Stepper. And so you can see a few revisions of this tool right here. Only the last week or maybe 2 weeks have we actually had it in basically a functioning state. So haven't done the actual lithography yet, but pretty close. So hopefully in the next week, if not two, start putting out something with this. A few things in the pipeline. Details don't really matter. There's a test exposure, doesn't matter. The big last thing I wanted to say is that we're bringing this to open source. So if you're in the San Francisco Bay Area, take a look at this, and I will see you there. Thanks for listening.
Great timing. Okay. Next. What was that? You, Tim?
No, that's him.
Wait up. This is you. All right. Okay. Actually, I might just pull this over a touch, so because it's hard to see the screen. Okay, cool. Ready? Go.
Sure. So recently, the open source silicon space had a bit of a setback with eFabless basically going under. eFabless at the time was the primary way people made open source silicon. We have multiple open source PDKs. There is the Sky 130 and the IHP one, but there's also one with GF 180 MCU. And I was always a little bit frustrated that eFabless never got around to offering that for manufacturing. And so with their disappearance, I decided I'd better get off my ass and actually do something. And so I've started a company called Wafer Space. The general plan is that it's the GlobalFoundries 180 MCU technology. It's about 20 millimeters squared. Our goal is to get you back over 500 raw die in under 3 months, and it'll be somewhere between $6,000 and $8,000 per slot on the thing. That's kind of the plan. I don't have a schedule yet, but I'm hoping to have one soon.
That's per 20 mil slot, yeah?
Yep.
Yeah. Okay.
And so you get back unprocessed die. The idea is that this only works if people actually buy slots. And so I'm planning to run a referral program which gets you either cash or credit, with the credit being that if you convince 6-ish people to do tape outs, you'll get your own free silicon effectively. And the big thing here is if you don't use it, this capability will go away. So if you're thinking about doing open source silicon, really think about doing it. Don't wait, because if there's a couple of runs that don't have enough people on it, there are not going to be any more runs. So yeah, sign up on the website to get notified when the details and stuff are available.
Great.
All right, sweet.
Ready? Go.
Hi, my name's Brian. I'm here to discuss the importance of free and open source silicon projects for agentic AI development. So a little about that. I currently work at Chip Agents. We are a new startup based out of Santa Barbara, started last year. And we are exploring agentic AI for design and verification workflows. Agentic AI is it's very adjacent to LLMs. Essentially think just like a bunch of LLMs with access to tools that can communicate with each other and then do things in a loop. I'm not an AI person at the company, so I don't know too much about that. But I do want to discuss some of the things that we are exploring in the hardware space. So one of my roles at the company is to figure out the best use cases for these agents in hardware. And one of the things we settled on was everybody needs help debugging, right? Debugging takes up so much time. And one of the things that takes up a lot of my time is just digging through waveforms and looking at them all day. And so it's an interesting modality because there's no other AI tools out there or whatever that really ingest in waveforms in any sort of manner, right? Maybe as an image, but that's iffy at best. And so that's something that we're exploring right now. And how do we convert these waveforms into things that are, I guess, parsable by large language models? And so, I mean, this is a really quick overview, but this is more so just an appreciation post for all the open source projects, because as a startup, I'm pretty much the only person in the RTL department, and so it's I really do have to rely on a lot of the open source software as well as designs to be able to do like the research aspect as well as the productization. So these are this is a non-exhaustive list of like projects that I've used in the past 6 months to help with my process. And so like things like Verilator, Surfer, OpenRoad, and the designs from like Pulp Platform, Low Risk, OpenPython, and BaseJump STL have been immensely useful for me. OpenTyne especially because they have like a UVM framework, and so not a lot of open source hardware has that, and so it's been really informative, great for me to learn about UVM. And so a quick thing that we've been working on is in software, there's this thing called SweBench, which is like a benchmark for essentially like using AI agents to like resolve PR issues. That's the main gist of it. And so something that like I've been trying to develop is waveform bench. So how do we convert that and ingest in waveforms and fix hardware problems?
No one's been like fully executed yet.
There's always a first.
It's not you.
Is it? Oh, is it good?
Yeah. All right. Ready?
That's me.
Go.
Okay. Hello, my name is Ethan. I went to school here at Santa Barbara. Now I am a lecturer at UC Santa Cruz, and next year I will actually be doing my PhD at Santa Cruz. Kind of a backwards kind of loop there, but okay. Show of hands. Anyone heard of Sky 130? Okay, probably most of you. Has anyone gone through into the repo of Sky 130, like look at the files in there? Okay, maybe a few less. So what you probably saw were some Spice files, some Verilog files. I guarantee what you did not see though, were nice schematics like these showing you how the transistors actually are connected. And if you want to know how a flip-flop is made or how an XOR gate is made, then what you'd have to do is you'd have to look at the Spice file itself and kind of reverse engineer how these transistors are connected. And so I've done that multiple times in my classes when I'm trying to teach students oh, here's an actual implementation of a flip-flop. And what I figured is well, maybe I should just put this all in a big repo and also get some other students to help me out. And so what this project has become is so far we have 50 of the 400 schematics currently implemented by hand. So this is kind of the flow that we have is first we run this nice little script that converts the Spice files into a nice kind of schematic template. Then students can go and organize them a little bit better and turn them into something nice. Then they can open a pull request. Also note that I'm using LVS through NetGen, if anyone has used NetGen. So these schematics are completely one-to-one with the official Sky 130 PDK. And yeah, so if anyone is interested in helping contribute, honestly, it's really satisfying to make these schematics. So if anyone has a long flight home or a long drive home and you need something to do, maybe just go and make a couple pull requests. I would be very happy. And I'm sure students at UC Santa Cruz would be very happy. So. Okay, I guess final thing is I tried at first to make the schematics automatically, but it is much easier actually just to do it by hand. I found all the layout and the algorithms are really just not great. So doing it by hand is generally faster and better, I found. So that's why, those are my opinions. So cool, okay, thank you everyone.
Thank you. Should have made the time limit shorter.
People have gotten better, I think. All right. Good to go.
You ready?
All right.
Go for it.
Hi, I'm Matthew Balance, and I want to talk about Python for verification and making the most of that with the test bench that you have. So a classic, CocoaTB test bench kind of looks like this. We've got a design, it's got signals, and that's the test bench. We bring Python in, CocoaTB, it connects directly to the signals. We might add a little randomization in, but we basically do all of our work in Python. But test benches come in all shapes and sizes. Your vendor might have given you a bus functional model for working with some complicated protocol. We're not going to rewrite that in Python. So how do you do? Do you just give up on Python? No. You actually can reuse that BFM, call it from Python. You can still drive signals with CocoaTB if you like, but you've actually got a much more complex, much more valuable test bench by leveraging everything you have. But what if you have a UVM test bench? You've got a lot of infrastructure here. You've got UVCs and VIPs and other stuff, a full UVM test bench. You can still put Python on top of that. You can drive all of your UVM infrastructure with Python. You can call Python from your system Verilog test bench. You get all of the value of your existing UVM with an additional value of sort of the dynamic nature of Python on top. So basically, no matter what your test bench looks like, you can add Python to it. That will add value on top of what you have. So it's a very scalable thing. Wow, I guess I'm fast tonight. So no matter what, make the most of Python in the verification environment that you have. Thank you very much.
Go for it.
Hi, I'm Larry. You've heard from me before. I've been hooking FPGAs up to computers for over 20 years. And it's sometimes a challenge to do that in a way that is robust and reliable and cost effective. I'm not a big fan of computers in the FPGA. It always seems clunky compared to the computer I have on my desk. So what I have here is something called Packet Badger that is used to connect the over Ethernet between an application FPGA and a commodity computer. You can, boy, it's going to be hard to read in the back, but it's GMII input and output, and then the UDP port plugins are meant to connect to actual hardware and do physical things on the chip. And one of the points here is that unlike an Ethernet router, a full packet has to be received and validated before you can actually act on it. You don't want to decide at the last minute that, yay, I turned the interlock on, but no, that packet failed CRC test. So we flow the data through one MTU buffer. This gives us everything we need to know about the packet before we act on it. So it's just a pipeline, and the name Packet Badger is a play because we put a badge in the dual port memory describing what the packet is. So on the reading side, we know what the packet is going to do before we start processing it and doing the whatever pushes and pulls and reads and writes that are defined. And this does include UDP, ICMP, ARP, so you can actually ping it, you can actually cook it up without any special software setup. In real use, you put this on the chip, it attaches to GMII, RGMII, fiber. This is where the plugins go. This is where you would actually do the real work, attaching to your DSP, what's the buzzword, CSR and all that stuff. So all of these would show up here, and now you can access them from the computer network. And I want to point out one crucial point. If you go away from here with just one lesson, you can bridge simulations of Ethernet to your local computer and physically ping it and ARP it and send UDP packets and do all the simulation of both Packet Badger and your application in Verilator. Ping time is like, I mean, you're used to ping times of half a millisecond. This is 5 milliseconds. It's a real simulation, real good for validation. The clients have a well-defined plugin. It's a robust means of attaching application-specific FPGA hardware to commodity computers. And I say FPGA, if somebody wanted to synthesize this, I bet it would work. This is a mature product. It's rugged, field-proven since 2019 with strong CI. Go for it. There's the documentation.
Thanks, Larry. Perfect. We'll take that. There we go. Okay. All right. Oh, Will. Will's up. Cool. Sorry.
Oh, I missed you. Sorry.
Okay. All good. That's cool. We're a fast, agile organization here at the Fossaf Silicon.
Cool. Yeah, so good to go? Okay. Hey, everybody. I'm Will Salcedo. And yeah, I've been wrestling with the open source tools for years, but this is like a just fun little project I did during my senior year. So does anybody know what Gem 5 is? Yeah, so basically what I did was I just wrapped DRAM Sim 3, which is the latency model for DRAM that's used in Gem 5. I basically just pi-binded it and then embedded it within PyMetal. So who here has heard of PyMetal? Okay, cool. And you probably haven't heard of it because CocoaTB kind of usurped it because it's mostly I would mostly use it for testing. So yeah, it's pretty cool. You can just basically I guess like simulate the like latency of DRAM memory accesses. So I'm sure there's more to it than that, but if this is something that can be useful to you, it's just like open source. The GitHub repository is up there, and my LinkedIn's down here too if you want to connect with me or whatever. So yeah, that's pretty much all I have.
Awesome. All right, cool. Thanks. Go for it.
All right, your documentation sucks. I'm not talking to anyone in particular, I promise. This is more of a rant about things that I've seen, and it's going to be very much oriented around like Python and Sphinx docs and stuff like that. These are tools that I love and use. So how do you fix it? And these are things that you should all take home, hopefully. First of all, know your audience. It's not enough to just put your project on GitHub. That's your first step. If you want anyone to use it, please think about documentation. People that are going to potentially use your projects, they want to know, is it worth my time? No one wants to waste their own personal time experimenting with something janky that they have never used before. So what's the maturity? Does it have tests? Is it abandoned? How do I start using it? And then where do I go for submitting bugs? How do I get help? And then also just show me the details. How can I get more information? I see these pitfalls everywhere, and we should do better. So first off, this is kind of the easiest. Cross-link everything. I've lost track of how many times I've found a really cool project on PyPy that's the top search result, and I'm like, okay, where is everything else? Who owns this? I can't even find the repository. So get that link to GitHub. Get the backlink as well. Same thing. Read the docs. That's a great way to host your documentation. Really richly annotated stuff. Cross-link that from the GitHub, and then also from Python, the package index, you can annotate links to your documentation as well as specifically things like releases, issues, and all that. Humans love this. Web crawlers also love this. I posted something on Read the Docs fresh page sometime last week. Within minutes, it was showing up in search results. API. If you have some kind of API interface, document it and document it well. This is your way to communicate to the world what you expect people to use, and it also implies what you don't want people to use. So especially with Python, you can muck around and actually reach into undocumented stuff, and if you change it, no one's going to yell at you because, well, you documented what you're allowed to use. Sphinx Autodoc is great for that. You can, if you actually put actual doc strings, and then also put some context around it so people can understand why. Sometimes APIs will just kind of be dumped out into the void, and it's like, great, but okay, we want more information. Lastly, make it look good. Making it look good makes it easy to look at. It's more approachable. Defaults are kind of a turnoff. Use a nice theme, paginate it, use pictures, make it look great. Thank you.
Amen. Yeah, completely. And that concludes the lightning talk.